we use scattergraphs to compare one result with another. So choosing which way round to plot the two axes, the x-axis is called the independent variable, or sometimes the explanatory, because it's the one that explains the behaviour in the other. If you breathe faster, it will might cause your heart rate to increase, whereas you can't just force your heart rate to increase to therefore increase your breathing. The y-axis is therefore the dependent variable, because it depends on what you do on the y, or is the response, the outcome of what happens. So there are various types of correlation depending on what pattern you get the crosses in. So anything that shows a trend going downward, so as x increases, y decreases, is called negative. And the closer the points lie to a straight line, the stronger the correlation. So this would be strong negative correlation, whereas this is weak negative correlation. Similarly, the crosses go the other way, so as x increases, y increases, we call that positive correlation. And the closer to the straight line, the stronger the correlation. Now this isn't just any correlation, this is specifically for linear correlation. We're looking at them being on a straight line. It might be they end up on a curved line, but that's something we're not going to explore for now. If the crosses just appear at random, then we say there's no correlation. If we want to interpret what's going on, we write as whatever the x increases, whatever is the y decreases or increases, depending on whether we've got positive or negative. So if we go back to this original one, the points lie quite close to a straight line, so we'd say it's strong correlation. It's going uphill, so it's positive, and our interpretation would be as breaths per minute increase, pulse beats per minute increase. Now, if we find that our points lie close to a straight line, we can then find a representative line. And we find this representative line by quite a complicated system of calculations. And it measures the distance of each point from the line and then tries to make those differences as small as possible. We call this the least squares regression. The squares comes from the fact that because some of these distances are above the line and some of the distances are below the line, so some are positive, some are negative, we square the values, which means we're only dealing with positive values. So we want to minimise the squares of all these distances with whatever line we choose. The equation for this line we write as y equals ax plus, sorry, a plus bx. Slightly contradictory to what we'd expect, because the straight line we're used to having as y equals mx plus c. For some reason, when we talk about linear regression, we've swapped them over and write it as a plus bx. So a is still the same function as the c, so it's the intercept, and b is the gradient. So if we are to interpret this, a is the value of y when x is 0, and b is the increase in y for an increase of 1 in x. We'll do an example of plotting the points and finding and plotting the line, and then we can do some interpretation. So here's a set of data about the hours of sunshine in 2 months. So we're going to plot all of this onto a scatter graph. So year 1 we assume comes first. So that will be our independent variable, and depending on what happens in year 1, that might affect what happens in year 2. That's what we're trying to find out. So my values run from 1.63 up to about 7. So 1, 2, 3, 4, 5, 6, 7. And on the y-axis, fairly similar. And then 2.0 goes with 1.64, 1.56, 1.6, 2.48, 2.78 is around to 2.8, 2.1, 5.6, 4.4, 7.3, 4.6, 5.5, 5.0, 4.8, 6.1, 4.7, 5.3, 3.6, 3.7, 1.9, 1.7, 1.8, 1.5. So if we look at the pattern, we've got some weak positive correlation. So the higher, or the greater the number of hours of sunshine per month in year 1, the greater the number of hours of sunshine per month in year 2, which makes sense as well with what you know about general climate, that 1 month, March in one year, has a similar climate to March in another year.